So this is s plus 1 over 3 g mu bar square. For example, I'm dealing per unit volume n over v. Here I have t minus z I s plus 1 over 3. The number of spins is cancelled out. 1 minus qa squared over 6. So what we see in the constant, it's a response on a magnetic field on a uniform one. Namely, where there is no Q dependence. We can put Q equal to 0, we get uniform magnetic field. Therefore, what corresponds to 1, this is a Curie temperature. I will keep writing numerator and denominator. So it's s plus 1 over 3 g mu bar square n over v. But here I have t minus tc, because this is tc, plus zi s plus 1 over 3 times qa squared over 6. Sorry? Question? Ask me. Where Tc, because for Q equal to 0, this susceptibility should diverge at Curie temperature, at Curie Weiss temperature. Plus so then we say that Curie temperature is equal to Z I S plus 1 over 3. So this is how Curie temperature is related to exchange integral. So suppose we have spin 1/2 and z equal to 6. So simple cubic means z is equal to 6. Spin equal to 1/2 means s plus 1 is equal to 3/4. If we then plug it in to the formula, we will get Tc for simple cubic spin 1/2 is equal to 6 times I times 3/4 over 3. So it is equal to 3/2 I. Okay? And you see that this is a Tc. So let me write my formula for susceptibility in a way that this is in denominator is equal to T minus Tc over Tc plus Qa squared over 6. And here I will write it as a Curie constant divided by Tc. Now I divided both numerator and denominator by the critical temperature. So this was particular example for square for simple cubic lattice and spin equal to 1/2. But of course you can take another lattice, take for example interaction not with nearest neighbors, but other interaction and see how to define Tc through the coupling constant and exchange integral, characterizing interaction with nearest and next to nearest neighbors. So now what we see, if we look at phase transition theory, I have variable tau. So then susceptibility chi q is equal to C over Tc, and here it's tau plus qa square of 6. You see the uniform part diverges at q equal to 0 as 1 over tau. So critical exponent, so chi q equal to 0 behaves as C over Tc 1 over tau. And if we define the critical exponent gamma, which says us it should be C over Tc 1 over tau to the power gamma, then gamma is equal to 1. This is a critical exponent describing us behavior of susceptibility at critical temperature. But remember, what we are dealing with now, this is a Tc, so T, and this is chi minus 1, we are studying this proximity. So we are above Tc, as it is written in the title of the lecture. Okay, what can we do next? Next, let's spend a few minutes for discussion. What does really this formula mean? By the way, this susceptibility, this form of susceptibility is known as Ornstein model. And when you discuss the fluctuations in the theory of phase transition, you will end up with that kind of correlator, which then allows to tell you when the main field theory is correct and when main field theory is not correct. Actually, what should we say? That this formula is correct, then tau is much smaller than 1. However, if you take into account the contribution from fluctuations, you will find a lower bound, namely the mean field theory, namely the such kind of brutal approximation when we replace the spin by its average value and we talk in terms of effective magnetic field, becomes incorrect if tau becomes extremely small. In that case, you probably know from Professor Silva lectures, then the scaling equations hold, and one can speak about critical exponents, and redefine them using very universal laws of scaling invariance. Did you discuss scaling invariance? So how coefficients, critical indexes, or critical exponents, alpha, beta, gamma, and delta are connected. So then we know. Experiment, for example, for the magnets, and I promise you to give an example of this magnets, tell you that this behavior with gamma equal to 1 is not very good when you come with a tau, say, smaller than 0.1. Then the behavior changes and gamma changes to 4/3. This is the value which comes from the scaling invariance. So it means that for real magnets, this kind of mean field theory, which we were discussing today, is not so good for small tau. As you will discuss on the theory of superconductivity, or you probably did it, the superconductivity theory describes real superconductors. I'm not speaking about high DC superconductors, pretty well until extremely small tau. because what is low bound and known as a Ginzburg number, so tau should be bigger than something, and I'm not going to derive you this something is extremely small in superconductors. Something like 10 to the minus 8, which means that the mean field theory is very robust and good, both qualitative and quantitative description, even in the very, very vicinity of critical temperature. The message which I'm giving you about magnets, that in real magnets it's not the case. Okay, let's make another comment. Let's look at this acceptability and write it down in a different way. I would like to write Q as some constant divided by Q squared plus kappa squared, where kappa squared is equal to what? I just multiplied it by 6 over A. It's 6 over A squared tau. So kappa is equal to 1 over A square root of 6 tau. Let's assume that this susceptibility, although being expansion for small q, what we did, we expanded our exchange integral in the vicinity of q equal to 0. Suppose that qualitatively this formula holds everywhere in your brilliant zone. And let's take chi r is the Fourier transform of chi q e to the power I q r dq, well, over 2 pi q. I don't care about it, about factor, so it's proportional to the integral over q squared e to the power, well, dq I q r, and here it's q squared plus kappa squared. So you see that kappa has a dimension of inverse length. And probably when we discuss the Coulomb interaction, and this shape of susceptibility is very similar to the shape of Coulomb interaction, you already screened Coulomb interaction. You already learned what this Fourier transform is equal to. Do you remember what it is? It's nothing but Fourier transform from screened Coulomb interaction. So it's Yukawa potential. So the Fourier transform is 1 over r modulus r e to the power minus kappa r. So this is nothing but Yukawa potential for screened Coulomb interaction. So what you see here, that this is 1 over r e to the power minus r over a, and here it's square root over 6 tau. Or let me define the letter psi, which is inverse kappa, which then is equal to a divided by square root over 6 tau. So this is 1 over r e to the power minus r over psi. The same. I just redefined the variable. So the psi is nothing but correlation length. What happens is when we approach to critical temperature, your tau, namely parameter which characterizes the vicinity to the phase transition point, and you are approaching from a disordered phase characterized by high symmetry to the ordered phase characterized by low symmetry. Then this correlation length actually diverges. So the index which characterizes the divergence of correlation length in the vicinity of phase transition is the index nu, and here for Landau or mean field kind of phase transition theory, nu is equal to 1/2. Again, for scaling theory, as you know, this mu is different, as well as the beta coefficient which we discussed and gamma coefficient which we have already discussed. So the correlation lengths actually characterize as the size of the system in which spins become correlated. Because this tells us by the susceptibility. So what happens if you approach it to the phase transition point? Although we are dealing with nearest neighbors interaction, so it's q equal to 0 or almost 0, and only nearest neighbors talk, closer to the phase transition point you are, bigger correlation length is. So more spins talk to each other, and when the correlation length approaches the size of the system, then all spins in the system know about existence of other spins. So to say, all spins become correlated, and this is how long-range order establishes. Okay? So this is why the concept of correlation length, which diverges at the phase transition point, but finally in the very vicinity of phase transition point, tells us how the long-range order established. In the next lecture, we actually associate this correlation function with a spin SV0, SVR correlation function, and see that in ordered phase, where the long-range order holds, this can be split into independent spins, because all spins look parallel, and this is a constant. So to say, this is square of order parameter. However, in disordered phase, where the correlation length is finite, then it cannot be split into this form, but behaves in this way. So when the correlation length is infinity, then the exponent dies, and one does have long-range order correlation between spins. Okay, was one comment. Let me now come back. Is it clear? Is it physically clear, physical picture? Because you will have pretty the same in the theory of superconductivity, where the concept of correlation length characterizing the size of Cooper pair is also very important. But here I have shown you how, first of all, Einstein-Zernike theory appears just from the mean field or molecular field treatment of the Heisenberg model. You may arrive at this Einstein-Zernike theory considering general fluctuations in the system, Gaussian fluctuations, and then you come to the same structure of the correlator. You can do it using Landau functional, and probably Professor Yevtushenko will show you how to do it. But this is just another example how to obtain it in the theory of magnets. What you can do in the fluctuation theory, you need to calculate the correction due to fluctuations, and this actually tells you how big fluctuations are in the system, and in the vicinity of phase transition they are huge. You need to calculate the correction to specific heat, for example, due to that kind of susceptibility. All thermodynamic quantities are connected, and you can express the correction to specific heat through this form of the susceptibility. And you see that the specific heat, which has a jump in the second order phase transition, acquires correction which grows and grows in low dimensions, namely in dimension 4 it grows logarithmically, in dimension 3 it becomes diverging, and then defining this fluctuation correction to specific heat be of the same order as a jump, you will arrive to this limitation that you tau, which controls the divergence of fluctuating correction should not be very small. So this is how this Ginzburg number appears. Sometimes it's called Ginzburg number, sometimes Ginzburg-Levenuk number, and actually it is expressed in terms of the correlation length as well. Good. So the message is, and you will probably, or you have probably learned it in the theory of phase transition, that if you come to higher dimensional systems, the fluctuations become weaker and weaker, and in principle, in higher dimension systems with the dimensions bigger than 4 for ferromagnets, you have mean field theory applicable everywhere. So you may ask me, how can we visualize higher dimensions? And this is also a very good question. In a seminal work of Larkin and Khmelnytsky, it was shown that effective theory for piezoelectrics, the systems which are characterized by spontaneous polarization, you can effectively have dimensions equal to 4. So then the theory requires logarithmic corrections, and one can construct a renormalization group, and so on and so forth. So 4 is upper critical dimension for that system, but of course, for low-dimensional systems, even for 3-dimensional systems, fluctuations become stronger and stronger in the vicinity of critical point. For the system with reduced dimensions, like dimension 2 or 1, fluctuations become so crucial that they destroy long-range order completely, and therefore, as we have already mentioned and as we have already discussed, the Merlin-Wagner theory holds, which tells you that for systems with a short-range interaction, and this is precisely what we do, we started with a model where only nearest neighbors interact and all other do not. The long-range order is not possible in the system in dimension 2 except temperature equal to 0, and in dimension 1 for arbitrary temperature. So this is precisely manifestation of importance of fluctuations, which play, as I said, very important role in low-dimensional systems. So before finishing this lecture, let me make few other comments. But look, I deliberately discussed with you only general and basic things. Of course, question about real system is very good, and at the end of the day, we are all about to describe our real world. But in order to describe real world, we need to separate what is of general importance and applicable to all kinds of second-order phase transition, and what is of less important and specific is for given system. For example, if you want to describe the behavior of nickel in the vicinity of localization, then of course you need to take into account type of crystalline structure, the spin of nickel, which is one, the way the nearest neighbor and next to nearest neighbors interact, and then you can come to quantitative description of the system. Moreover, I told you that in typical magnets, Curie temperature is of the range of 1000 Kelvin, so it's by the order of magnitude higher than room temperature, or yeah. But this kind of behavior, namely divergence of susceptibility, this Arstein-Zernike thinks divergence of correlation length and establishing of long-range order are general for every magnetic transition, for any magnetic transition, and therefore, before coming to description of system, and I don't think I will be able to discuss any real system during my lectures, I give you general information about this. Okay, let's come back to IQ, which was equal to 2Li over n, and here it's cosine ux. A plus q, sorry, cosine uy, a plus cosine qz. So let's take extreme system, namely one-dimensional system. in 1D in order to reduce number of variables. IQ would be just 2I over n, and here it's cosine u. And we saw that susceptibility, which was 1 minus here, what was that? It was I u times n times chi naught over g mu bar square, and there was something here, basically chi naught. So this was a structure of chi q. It, as I said, diverges at critical temperature for some given q. So if we plot this IQ, so this is pi over a minus pi over a, and this is IQ as a function of q, right? You see the divergence of susceptibility is happening at zero momentum. So our state serenity tells us that susceptibility diverges as 1 over tau at q equal to 0, and then the fluctuations are described by this q squared term. Actually, if you have more complicated model, which involves not only nearest neighbors but next to nearest neighbors, and the sign of exchange integrals I1, I2, I3 is the same, namely positive, you will always have divergence of your susceptibility at zero magnetic moment. And it corresponds to ferromagnetic ordering of the system. However, suppose for the moment that we took exchange integral being negative. As I said, let's say that I rho is equal to minus modulus I for rho equal to A, and otherwise we can still use the formula. We can still use the formula there, but IQ will be of that sort, so it's pi over A minus pi over A, IQ as a function of Q. So the divergence of susceptibility happens not at zero momentum. At zero momentum, IQ is not maximum but minimum, but at the wave vectors corresponding to reciprocal vector. So if we look at susceptibility chi corresponding to Q equal to 0, we will not see any divergence anymore because I is negative. And this is what is known as Néel law. So susceptibility Q equal to 0 is not divergent. Sometimes antiferromagnets, and this is subject to Néel law, are discussed as a ferromagnet with negative Curie temperature. Because if you plot chi minus 1, it will not diverge at positive axis of temperatures, but rather at negative 1, although negative temperatures do not have any physical meaning. However, the antiferromagnets and uniform response on the antiferromagnets correspond to that kind of susceptibility. So in addition to Curie-Weiss law, we now have a Néel law. Néel. So Louis Néel was a French physicist, one of the fathers of theory of antiferromagnet. However, at the wave vectors corresponding to reciprocal vector, namely pi over A and minus pi over A, the system is inverted and it behaves like in a ferromagnet. So for antiferromagnets, the Einstein theory holds in the vicinity of reciprocal vector, Q minus Q for small deviation from this point, and it has pretty the same form where tau characterizes as vicinity to nail temperature. So susceptibility diverges, but this is not uniform susceptibility. This is a response to alternating magnetic field. The magnetic field, which just flips its direction in every lattice side, so the lattice spins wants to be anti-parallel, and therefore this kind of alignment of spin corresponds to the antiferromagnetic order. So for antiferromagnets, as I said, the uniform magnetization and uniform response, uniform magnetization is equal to 0, and uniform susceptibility is not divergent. But staggered susceptibility, which is the difference of magnetization on two sublattices, so well, the reciprocal vector is involved, we do have to speak about two sublattices, behaves as an order parameter, namely staggered magnetization is non-zero below TC. So it corresponds to spontaneous symmetry breaking on the different sublattices. So staggered magnetization, or sometimes people speak about nail order, is non-zero below nail temperature, corresponding to antiferromagnetic alignment of spins, and 0 above nail temperature. And the response function becomes divergent at the wave vector corresponding to reciprocal one. So this is how, from general theory of Heisenberg magnets, I did not specify actually positive value of constant at the very beginning. I just arrived at the conclusion that if I is positive and nearest neighbors interact, I come to the divergence. But repeating the theory, I can describe correctly the behavior of antiferromagnets. You may ask me what happens if the exchange integrals are of different sign for nearest neighbors and next nearest neighbors. This would be a very good question. Then the magnetization, then the divergence of susceptibility is occurring at some non-zero wave vector, like for antiferromagnets. And this non-zero vector is defined from the condition that 1 minus I Q n chi node over G mu bar squared is equal to 0. This equation defines as both critical temperature and the wave vector in which our susceptibility diverges. Then we arrive at some helicoidal structure on a spiral structure which describe more complicated and more complex magnets. So in the next lecture and the lecture after the next, we will discuss in more details theory of ferromagnets and antiferromagnets and temperatures much below critical temperature. So at temperatures close to absolute zero, and we see what are the excitations in the system called magnons, how to visualize these excitations and what they are corresponding to, what is the difference in excitations of ferromagnets and antiferromagnets, and what is the manifestation of Goldstone and Bergen-Wagner theory in this kind of one sublattice and two sublattice magnets. Okay, that's all for today. Any questions? So if not, we meet tomorrow and continue. So at the end of this week, I hope to be able to give you the homework.
the index. Because the bigger the subgroup, the smaller the index. That's the problem. Identity, the subgroup as order 1. So what is the index? It's 8. So it will fix the big one. It will fix the big one. At least you make me know. No, it's very easy. And you should be able to maybe, because somebody can just give you some code. Yeah, no code looking like f of x. Because it makes f of plus 3. Just tends to illustrate, like when I will say x. That was nobody does.